Welcome back to Integral Calculus. In this video, I want to talk about arc length. That title kind of says what it wants to do if we can make sure we understand it. The idea of length is something I think at this point in your mathematical journey you are incredibly familiar with. When we're talking about length, we're talking about the distance along a path. When we're talking about an arc, that's where I think you have an intuitive understanding of what we mean, but let's give it a formal definition. An arc, in terms of what we're going to be working with right now, is any smooth curve. All right. Well, we know what a curve is. What does it take to make a curve smooth? Again, this is a definition that probably has come up previously in your study of calculus, but it's one of those things that we tend to gloss over because we just work with it. Right? At this level of mathematics, we kind of assume that all curves are smooth, and we just assume everything is going to work nicely. But when we say a smooth curve here, we specifically mean that we need a curve where the derivatives exist. We can differentiate this curve as many times as we need to in order to get the tools at hand to work. All right. So we have a smooth curve, and we want to know how long the curve is. That's a long way to go to get something that you probably were able to intuit just looking at the title of the video. But now that we're on secure footing, let me get my head out of the way and let's try to analyze some of these details. The best tool that we have for analyzing lengths is the distance formula. The length of the line segment between the points x1, y1, and x2, y2 is the square root of x2 minus x1 squared plus y2 minus y1 squared. It's basically just the Pythagorean theorem. And that gives us the distance around or across this straight line. If we have a curve that we are working with, then we sincerely hope that that curve comes in the form of an arc of a circle. Where we can say that the arc length is the radius times the angle. When I was a student, I was convinced that that second formula, arc length, should be the thing that we are trying to generalize in order to find the distance across an arbitrary curve, but it turns out that that's actually quite challenging. It is the distance formula that gives us the best tool for success. All right, so let's consider a smooth curve. I'm just going to look at this arbitrary looking shape between this point and that point. One of the things that you might try to do if you are trying to find the length of this curve is approximate it using a straight line. And if we use a straight line, we can use the distance formula, so that's nice. The problem with that is that clearly that's a different path. But what if we used a couple of straight lines? What if we stopped at a couple of points along the way and calculated the straight line distance between each of those points? Well, it's not perfect, right? There's spaces here where it is clearly different from the original curve, but it's not that bad. And if we introduce a whole bunch more points, Well, now it's getting really good, right? I've got some places here that don't look good, but that's honestly more my ability to draw on a touch screen than it is the fault of the approximation. So, if we break the curve into endpoints, calculate the distance between each pair of points, and add all of these distances, then we're going to get a pretty good approximation of the length of the arc. And we're doing it by calculating straight line distances using the distance formula, which is something we are very familiar with using. And if we choose a bigger value of n, we get a better approximation. Well, this is calculus, so there's no limit to bigger value of n. We can choose the biggest value of n we can. We can take the limit as n goes to infinity, which will, in theory, give us a perfect approximation. And that's what we're going for here. All right, so if we have a point, the x-coordinate will be x, the y-coordinate will be some f of x. Then the next point is going to be x plus, I'll go ahead and call it delta x for now. This is eventually going to become our differential dx. And then we'll evaluate f at x plus delta x. Then the distance between these is going to be the square root of the difference in the x-coordinates, x plus delta x minus x squared, plus the difference in the y-coordinates, f of x plus delta x, not comma, minus f of x, again, squared. And if some of these things are looking a little bit familiar to you, that is entirely intentional. I've got a couple of x's here that are going to cancel each other out, so that I have delta x squared plus f of x plus delta x minus f of x squared. Now the next thing I'm going to do is not immediately obvious. Some of you probably already see it. If you don't, that's not a problem at all. I don't expect you to. But after I do it, it should make sense why I did this. I am going to factor out a delta x squared from both terms in the denominator. When I do that, I will get that this distance is the square root of 1 plus f of x plus delta x minus f of x all over delta x squared. That whole thing multiplied by delta x squared, and all under the square root. Why did I do this? Well, the first reason that I did this is that this delta x squared can now come out of the square root, right? I've changed the stuff under the square root from addition to multiplication. And when there's multiplication, you can split it up. The square root of delta x squared is just delta x. But the real reason that I did it, and something that you are probably looking at already, that is the difference quotient. If I take the limit as delta x goes to 0 of d, we're going to call that the arc length. We'll call it little s. And we can bring the limit inside. And that is the definition of the derivative. So we're going to have the square root of 1 plus f prime of x squared. And the limit as delta x goes to 0, we'll generally write as dx. All right. So this is just one piece of the arc length, some little differential in the overall arc length, but that is in fact the entire idea. The actual arc length is going to be the integral from the starting point to the ending point of the curve of that little piece of arc. And we get to the bane of calculus students everywhere. I spent, 5-7 minutes going through this. I used the definition of the derivative in order to get a formula that contains an integral. And not just any integral, an integral of a thing underneath a square root. By and large, this is going to be an incredibly challenging integral to work through. We have to get really lucky with the particular function that we're studying in order to be able to evaluate it. But you're in my classroom. Of course, we're going to get really lucky with the first thing that we want to try to evaluate. So consider the function f of x equals 2x to the 3/2 power from x equals 0 to x equals 1. If I want to analyze this curve, the first thing I'm going to do, I didn't mean to bring myself up on this, the first thing I'm going to do is jump into something like Desmos. I am going to graph this curve. So here we have the graph, and I have in white the entire curve. You can see it starts at 0, 0, and continues upward in a not quite parabolic arc. I have the stopping point of the arc we care about, which will be 1, 2. Just plug in x equals 1, you'll get out that y is equal to 2. And the part that we're going to actually care about finding the length of, kind of right there in, I don't know, I think that's a greenish color, but as I've mentioned before, I'm colorblind, so don't quote me on that. Before I dive into anything else, the first thing that I notice here is that this is relatively close to a straight line. So if I come up here and add in one more line, right, the line between 0, 0 and 1, 2 is y equals 2x. Let's make that a much more contrasting color because I can't tell those colors apart. There we go. We'll make that straight line in blue. Right, so the straight line distance is not that bad of an approximation. I'm going to do that before I do anything else. If I jump back over to my notebook, we're going to look at the straight line distance from 0, 0 to 1, 2 is the square root of 5. In almost all applications in this course, I would leave my result like that. But because I'm going to be trying to compare some numbers, that's a difficult comparison. I'm going to grab out my calculator, and I'm going to make note that the square root of 5 is approximately equal to, I'll call it 2.236. We know that the result we end up with should be bigger than 2.236. If it's not, that's a sign that something has gone wrong. Great way of setting up so that we can double check ourselves later on. All right, so to use the arc length formula, we are going to need to differentiate. So our function f of x is 2x to the 3/2 power. F prime of x is going to be 2 times 3/2 times x to the 3/2 minus 1, which is 1/2. And I guess we can clean that up and write it as 3 times the square root of x. That's probably the nicest way of writing it. And we want to find the arc length, which is going to be the integral from x equals 0, our starting point, to x equals 1, our ending point, of the square root of 1 plus our derivative, 3 square root of x squared. We know that x is going between 0 and 1. It's always positive. We don't have to worry about any weird things happening here. We can simplify this quite nicely. Three squared is 9. Square root of x squared is x. And if you've spent a lot of time working with integrals, you can probably do this directly, but I think it's going to be easier to put in a u substitution. We'll set u equal to the stuff under the square root, 1 plus 9x, which means that du is going to be 9 dx, and I can rewrite this integral as the integral from, well, when x is 0, u is 1, and when x is 1, u is 10. And then we have the square root of u du. Although at this point, I think it'll be easier to write this as u to the 1/2 power, because that way we can just continue in here. I'm forgetting something. I forgot to include this 9. All right, so we need to get a 9 in here, which means we need a 1/9 out here. There we go. Now it should all make sense. All right, so we get our arc length is 1/9 times 2/3 u to the 3/2 evaluated at 1 and at 10. All right, so 1/9 times 2/3 is 2/27. And then we're going to have 10 to the 3/2 minus 1. And once again, in almost all applications, I would be happy to leave that here. Maybe I would rewrite this as 20 square root of 10 minus 2 all over 27. But that's how I would leave my result. But I want to compare. I want to make sure that this is bigger than the square root of 5. So let me grab out my calculator once again, and we'll punch that in. 20 times the square root of 10 minus 2 all over 27. My calculator tells me that that's 2.268. So we got that our arc length is 20 root 10 minus 2 all over 27, which is approximately 2.268. And when we did our easier approximation, we got 2.236. So yeah, our result of this arc is a little bit longer, but not a lot longer. And that's what we expected, right? If I go back to the graph, remember, the straight line distance was not that far off of the actual curve, so we didn't expect to see a significant change when we actually calculated the true value. Being able to calculate the true value is what it's all about. Before we wrap up, I do want to address one more time the integral formula for arc length. If I scroll way back in my notes, there it is. This is a hideous formula, right? A square root with addition under it and a function being squared. In most circumstances, an expression like this, given an arbitrary function, you are not going to be able to evaluate the integral by hand. Sometimes, like with the example I went through here, it works out relatively easy. Sometimes there is a trigonometric substitution or something along those lines that will help us out and get us the expression we're looking for. But most of the time, we kind of just have to throw our hands in the air and say, I don't know. A little bit later in this course, I'm going to look into addressing a way of handling that when circumstances don't allow. But for right now, we're just going to accept it. And we're going to accept that an answer given in the form of an integral is perfectly fine if nothing else can be done. On homework, on quizzes, look for that sort of information. Right? If I don't think that the integral can be evaluated, I will tell you, this integral can't be evaluated. Don't try to evaluate it. If I tell you to evaluate the integral, that means that I expected that there is a way to do it. That might be a straightforward way, that might be a little bit more challenging. I don't really know. I haven't written the assignment yet, but pay attention to that difference. And so with that in mind, I would like you to solve up to an integral. For the length of the curve, f of x equals 2x squared minus 1 over x between x equals 1 and x equals 5. Right, so again, please don't try to take the time to actually evaluate the integral. I don't think it's going to be possible. Or if I set this up correctly, it shouldn't be possible. But see what you can do setting that up. Make sure you understand the basic concept of arc length, and I'll see you in the next video.